Hello, this is Jack Jackson. Today we're going to talk about linear functions. Linear functions are probably the single most important class of functions for a number of reasons. One is because there's so many real-world phenomena that can be modeled very closely by linear functions. And a lot of things that aren't linear can be modeled by linear functions if we restrict to a very short period, say short period of time, for example. And so linear functions, not only are they got one of the most simple graphs in the world, of course just a line, they also have a lot of nice structure in the formula and the table and the graph, and all these things are relatively simple, so it's a good place to start, and it's also the most applicable class of functions to look at. So our outline here, we're going to basically break this video into two parts. The first video, we're going to talk about basic concepts. We're going to talk about the idea of extending the domain of arithmetic sequences to all real numbers. So we're going to assume that you've done some work with arithmetic sequences already. Then we're going to develop a general formula for slope. And then we're going to understand the structure of linear functions, more about the slope. And then we're going to understand the structure of the table, the graph, and then several versions of the formula or equation. We're going to talk about the slope y-intercept form, the point-slope form, the slope x-intercept form. We're going to talk about finding an equation given 2 points. And we're going to summarize all of this information. Then in the second video, we're going to look at some applications that directly relate to these different techniques and concepts. So the first thing you want to do now is be sure that you've done some of the previous material that I'm assuming that you've done before this. The first is that you've gone over the material in the arithmetic sequences section, because that really develops the foundation for what we're going to do here. And we're going to generalize a lot of what we saw in that project that we worked on there and the other videos and things that summarize what we learned about arithmetic sequences, because what we're going to do is extend the domain of arithmetic sequences to make linear functions. So all the structures we saw there are going to come forward. And then there's a Minds On project on linear functions. Minds On Linear Functions project, introducing the structure of the table, graph, and formulas. And this is in the same section in Blackboard. You need to be sure that you do this section first, do this project first, and you can even check your answers with the included solution set before you go into this video. Okay, or at least try those first, and that includes using the related GeoGebra investigations that are there. So if you have not finished those things, stop this video right now, go do those things, and then come back to before you watch this video. So when we go from arithmetic sequences to linear functions, what we're doing is we're just extending the domain. So remember that in a sequence, the domain is just the natural numbers. So when we look at this, we have isolated points in our table with nothing between those points in the table. We have a first, a second, a third, and a fourth point, or a first, second, third, and fourth term, and so forth, and it goes on forever. But there are nothing in between. There are no negative terms. Sometimes we have a zero term, sometimes we don't. And if you graph these, you get a bunch of points, a bunch of isolated dots. But if it's an arithmetic sequence, those dots are all in a straight line. So if we extend the domain to be all real numbers, we're just going to connect the dots and make a solid line. So a solid, straight, connected, continuous straight line is our graph, and this extended function is called a linear function. Of course, it's named after the shape of its graph. So notice when we change from arithmetic sequences to linear function, you can kind of see on the left kind of a review of what we learned about arithmetic sequences, and on the right how this extends to linear functions. Mostly it's just some notation change in most of the things, and there are some substantive differences. Really, the main substantive difference is in arithmetic sequence, the domain is just the set of natural numbers, or possibly the set of whole numbers. In linear functions, however, the domain is a set of all real numbers. So we can look at all real numbers there, and that makes it a connected line when we graph it. So the range is this discrete set of outputs whereas the range is going to be the entire set of real numbers for a linear function, well, at least as long as the slope is not 0. If the slope is not 0, that degenerates to a constant function, which we've already studied, which of course is a horizontal line. The range would just be a set containing one single number. But if any other kind of linear function, the range is going to be the set of all real numbers. So, in an arithmetic sequence, again, a graph was a discrete collinear points. So the points that were all in a straight line, but it wasn't a connected line because they're all spaced apart, one horizontally with nothing in between, but they're also spaced vertically m units. So as we move from one point to the next, we're moving to the right one, and we're moving up or down m units. If m is positive, we're going up. If m is negative, we're going down. And so when we have our solid straight line graph for a linear function, again, if we take any point on the graph and we go to the right one, then we'll go up m units, or we'll vertically change of m units. Again, if m is positive, we're going to go up m units. If m is negative, it'll go down that many units. In the table of an arithmetic sequence, of course, the input being sequence, the input's just 1, 2, 3, 4, 5. Sometimes 0, sometimes not. Well, we'll just say for right now it starts with 1. And then the output, what we see is it goes up by the same amount each time. It has a common difference. This common difference, I use the letter m because it's usually referred to as m when we get to linear functions, and that's called the slope. And some books will refer to this as d when they're dealing with an arithmetic sequence, but it's the same thing as m. It is the slope, it is the common difference, it is delta y whenever delta x is 1. We're going to see in the next few pages here that in general that the slope is a constant rate of change. It's delta y divided by delta x between any 2 points on the function when it is a linear function. Arithmetic sequences, we can see this adding the slope each time in the form of a recursive formula. We specify the first term, a1 equals some number, whatever a1 is, and then to get a sub k, it is a sub k minus 1 plus m. That's a typo. That should say k minus 1 should all be in the subscript. I'll fix that before I print it out for you, for your notes. A sub k equals a sub k minus 1 is all in the k minus 1 is all in the subscript there, plus m. So in other words, if we want to find a particular a value, we go backwards 1 in the table to the previous k, find its a value, find its term, and add the slope. So we just add the slope each time. And this would work for any point here in the linear function. If we want to find f of x, if we could just find f of x minus 1, then we could add the slope to that, and that would give us our output. Of course, what we'd like to have is a non-recursive formula. So if you have a sequence starting with the first term, you could have sort of a point slope formula here that says a sub k is m times k minus 1 in parentheses, plus a sub 1. If you distribute here and combine like terms, you get it in the form a sub k equals mk plus a sub 0, and a sub 0 is the 0th term, which may or may not actually exist in the function, but we can figure out what it is. It's just a1 minus k. Now back in the recursive formula, you could actually specify any point that you want, and instead of the first point, and it would still work. Specify any term. As long as you know the term number that goes with it, you could work this out. In the non-recursive thing here, we could also center at some other points, but we have it written like this, so we have a couple versions of the formula. We're going to see that non-recursive formulas in linear functions, we have one like the last one here on the arithmetic side, and it's called the slope y-intercept form, or just the slope-intercept form a lot of times, and that's f of x equals mx plus y sub 0. If you notice, it's the same formula, I've just changed the notation. Instead of using k for the input like I do for a sequence, I use our more common x for the input for linear function. Instead of calling the 0th term a sub 0, I call it y sub 0, which is the y-coordinate of the y-intercept. So notice in this form, and the m is the slope either time. And then instead of calling it a sub k, or f sub x. We call it f of x. Of course, that's our standard function notation. Similarly, we can have a slope x-intercept form, which is also a factored form, which is m times x minus x sub 0, the x minus x sub 0 in parentheses. We can also have a point slope formula that's more like this first formula that we have over here for the sequence. It's f of x equals m times x minus x1 plus y1. We'll talk about all these forms of the formula here in just a minute. Before we do that, though, let's talk a little bit more about the idea of a slope. Now here we have basically an arithmetic sequence, although it could be just part of a continuous linear function, which is the way we're going to think of it here. But we can use our same techniques we learned about arithmetic sequences for this example. So remember, if delta x is 1 and f of 0 is in the table, in other words, the 0th term is there, and we're not skipping any terms in terms of a sequence, we can find the slope y-intercept form of the equation pretty easily. So is this linear or not? And if it is, compute the slope y-intercept form of the equation and graph these points that you see in the table on a piece of graph paper, and then get your straight edge out to connect to make it a linear function. And then use the formula that you come up with to compute f of -1, f of 1.3, and f of 100. Notice that if this was an arithmetic sequence, f of 100 would be in the sequence and it would be there somewhere, but there would be no -1 term or 1.3 term, so the first two would not make sense for an arithmetic sequence. But if we generalize this to the domain being all real numbers, then this makes sense for a linear function. So what I'd like you to do is go ahead and work this one out. You should know how to do this based on what we've done earlier. And then come back whenever you get that done, and we'll check this out and then generalize this a little bit. So press pause now. Okay, well now you're back. You should have worked this out. Let's take a look and see. Well, if you notice, notice that the delta x is 1 each time. We're going up by 1. And then you look at the y's and find the differences. 7 minus 3 is 4. 11 minus 7 is 4, and so forth. So if you notice, each time we're adding 4. 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 15. 15 plus 4 is 19. And 19 plus 4 is 23. So all the way up and down the table, we're just adding 4. And so that delta y is the slope because we're going up by 1s on delta x. So the slope is 4. And so, and the y-intercept is 0, 3. That's quite right there in the table. So the formula is y equals mx plus y sub 0, or f of x equals 4x plus 3 in this particular case. So that was pretty easy to do. We see the 4 because it's how much we're adding each time to the y, or f, or output, to get the next output. And 3 is our initial value. That's our y-coordinate of our y-intercept. That's the y value that goes with an x of 3. And of course we could check this out. Of course we plug in 0. 4 times 0 plus 3 is 3. That works. Plug in 1. 4 times 1 is 4 plus 3 is 7. Plug in 5. 4 times 5 is 20. Plus 3 is 23, and so forth. So it works. And if you graph these and connect the dots, you get a solid straight line, and you can see that here in the graph. And now if we want to compute f of -1, that's 4 times -1 plus 3. 4 times -1 is -4 plus 3 is -1. Makes sense. If we plug in 1.3, we can find f of 1.3. 4 times 1.3 plus 3, let's see, that's 4 times 1.3 is 5.2 plus 3 is 8.2. And if we do, that's the last one's supposed to say f of 100 is 4 times 100 plus 3 is 403. I'll fix that typo before we do a printout. Okay? But now what if we have a situation like that? So that last example was all well and good. That's exactly what we've done before. But what if we get a situation like this one where delta x is not 1 in the table and f of 0 is not in the table? Can we still recognize if it's a linear function or not? And can we, if it is, how can we compute the slope? So how can we determine if this table is linear or not? Well, one thing we might do is start by computing delta x and delta y. So notice the first time we go up by 2 on the x side, then 7 minus 4 is 3, so we're going up by 3 the next time. and then from 7 to 11 is 4, 11 to 15 is 4, and 15 up to 20 is 5. So we don't even have a consistent delta x. So what do we see for delta y? Well, we see the first time is 6, then 9, then 12, then 12, then 15. Of course, how did I find that? 15, I found that by 67 minus 52. And I found the 9 by 28 minus 19. In other words, 19 plus 9 is 28. So, well, we're not seeing a consistent delta y. One thing is encouraging is notice that there were two of them when delta x was the same, and for those two, the delta y was the same. So that seems like it might be something that's linear, but we really can't tell yet. What could we do here? Well, we know if we were to write this out all the way where delta x is 1, and if we could find a slope that was a delta y that was the same every time, and sort of fill in the blanks here, if that delta y was the same every time, then that delta y would be the slope. Okay, but it has to be only, not the delta y. Well, like in the last one, delta y can't be the slope. It's not, the delta y's aren't even the same, of course, because I'm sort of skipping around here a little bit. Not going up by the same amount, or not going up by 1. But if I go up by 1, then I know that that delta y, if it is the same, is going to be the common difference, and it will be the slope. So let's see what we've got here. We're going from 13 to 19. In 2 steps, we have to add the same thing twice and get us up to 19. So it's a total step of 6, but we want to do that in 2 equal pieces. What would that be? Or look at the next one. We're going to go up from 19 to 28, which is a distance of 9, and we want to do that in 1, 2, 3 steps. So how do we do? How do we figure that out? Well, let's think about that a minute. So we want 13 plus whatever m is to be the next blank right here. And we want to take that and add m to it, and we get 19. So 13 plus m equals 19. So m plus m, a shorthand for that is 2 times m. And of course 19 minus 13 is 6. So 2 times m is 6, so m has to be what? Okay, 3. You probably already had that figured out. Similarly, when we go from 19 to 28, we're doing it in 1, 2, 3 steps. So 19 plus m plus m plus m is 28. So 28 minus 19 is the 9. That's our delta y. But we have 3 steps, 3 times m. By the way, 3 was our delta x. 7 minus 4 is 3. The first time, 4 minus 2 was 2. So that delta x is how many steps we're going up here. And of course, we simply divide and get 3. So if we fill this in, look, it does work. Delta y is 3 every time. 13 plus 3 is 16, plus 3 is 19. That checks. 19 plus 3 is 22. 22 plus 3 is 25. 25 plus 3 is 28. I believe that was one of the ones we had. And so forth, and you see that it works all the way up and down. So in fact, this is a linear function with a slope of 3. Now, this is a little cumbersome to have to actually fill this whole table out every time we want to figure one of these out. Let's see if we can look for a shortcut. One of the things about algebra we like to do, one of the basic algebraic habits of mine, is to look for patterns and then see if we can formalize those patterns into some shortcut rules that allow us to get there a little faster rather than having to write this whole table out each time. So let's look back at what we started with. We had our table, here we go, 2, 13, 4, 19, 7, 28, and so forth, of x and y's. And then we found delta x and delta y. So the first time, delta x was 2, delta y was 6. Now we know ultimately the slope was 3. So how can we use the 6 and the 2 to find the 3? Okay, the next time we found delta y is 9 and delta x is 3. How can we use the 9 and 3 to get the slope of 3? Next time, the delta y is 12 and the delta x is 4. We got a 12 and a 4, and we got to get 3 out of that. How do we do that? Well, hopefully what you realized is every time you just took the delta y divided by the delta x to find the slope. And so that's going to be our definition of the slope. It's delta y over delta x. So in other words, if you have a point x1, y1 and another point x2, y2, delta y is y2 minus y1 and delta x is x2 minus x1. And we divide those two things, delta y on the top, delta x on the bottom, And if we divide those out and we get this, we get a slope m. So that's going to be the slope between 2 points. If that's the same every time, which it actually is here, right? 6 divided by 2 is 3. 9 divided by 3 is 3. 12 divided by 4 is 3. Another 12 divided by 4 is 3. 15 divided by 5. Again, 3. 3 every time. So the fact that all those were the same, that makes it linear. So the slope being the same makes it a linear function. So, in general, we'll define the slope between any 2 points, that is, ordered pairs of real numbers, x1, y1, and x2, y2, from a relation generated in any way by a table, graph, formula, whatever, between real number, input and outputs. It's going to be defined to be, we'll use the letter m, lowercase m for it, and it's defined to be delta y over delta x. And of course, by delta y, we mean y2 minus y1, and by delta x, we mean the difference in the x's, or change in x's, which is x2 minus x1. Notice that this is a ratio, or division, or fraction, of changes. We have the vertical change, delta y, on top. It's how much, as you go from, like if you go from point 1, the x1, y1, to point 2, x2, y2, delta y is how much we moved up or down. If delta y is positive, from point 1 to point 2, we went up. If delta y is negative, from point 1 to point 2, we went down. And then the delta x in the denominator is the horizontal change. It's the difference in the x's, x2 minus x1, or the change in the x's. That's a horizontal change. If delta x is positive, we went to the right from point 1 to point 2. And if delta x is negative, we went from the left from point 1 to point 2. So what we have is a ratio of changes, or a rate of changes. And this is actually an average rate of change between the 2 points. So in a physical setting, contextual setting, then the slope is going to be interpreted as an average rate of change. Now this is true for any 2 points from any relation. It doesn't have to be linear. But the problem is when you take 2 points from one relation and then you take another 2 points from the same relation, you could get 2 different values for the slope. But not if it's a linear. If it's linear, the slope between any 2 points is the same. And it turns out that if you get, like this example over here, when we did the first 2 points, we know that there's exactly one line that goes through this first 2 points. There's always a line going through any 2 points. And there's a line going through the second 2 points. But the fact that those two had the same slope and they share this point 419 in common means that those first 3 points are all on the same line. And the fact that we got a same slope on the next 2 says those next ones are on the same line, and so forth. So in fact, if we take any 2 points here, we'll get the same slope. So we did it with successive points, but if you took, for example, 20, 67 and 4, 19, for example, you'll get different delta x's and delta y's than we had here, but when you divide, you're going to get the same slope. So, in big red letters here, linear functions are functions with a constant average rate of change, or a constant slope. That's going to be the main thing about linear functions. So let's take a table and finish finding our formula. If you look, we've already found the slope, but we haven't found a formula yet. We need to know something about it. One thing we can do is just use a point slope formula and put in a point here. So the formula is y, or I'll use f of x here because that's the label that was given. F of x equals m times x minus x1 plus y1. So f of x equals m was 3, parentheses x minus, well, pick a point. I picked the second one, 4, here, plus the y of 19. I could have also written 3 times x minus 2 plus 13, or 3 times x minus 15 plus 52. I could pick any of the points that are in the table. Now make sure this works, okay? Let's put in 4 here. 4 minus 4 is 0, times 3 is 0, plus 19 is 19. So that makes sense that those go together, right? The 4 here and the 19 here. Okay, the subtraction needs to be built in so that it'll cancel this out when we put the 4 in. Now let's take another point, 7. 7 minus 4 is 3, times 3 is 9. 9 plus 19 is, sure enough, 28. And you can check this for all these points and see that that does work. Now if I use the distributive property and then combine like terms, I get 3x minus 12 plus 19 Negative 12 plus 19 is 7. So this reduces or simplifies, if you will, to f of x equals 3x plus 7. Now this is the slope y-intercept form. Y equals mx plus y sub 0. Some of you may be familiar with somebody calling it y equals mx plus b. But I like to use y sub 0 instead of b because it really is the y-coordinate when x is 0. So y sub 0 is more suggestive. And we might reserve b for something else later on. So this works out pretty nicely. Notice that the point slope formula is not unique. There are many, many different points we could center this up at. In fact, any one in this table or any real number, we just put the appropriate x and y together, we can get this to work for any point on the graph. But there's only one y-intercept form, slope y-intercept form, and there it is. Sometimes this is just called the slope-intercept form, but probably the slope y-intercept form is more appropriate because there also is a slope x-intercept form, and that's what we're going to look at next. And basically, if we'll just use the distributive property to take this slope y-intercept form and factor the slope out, then we get, we pull the 3 out front, and of course we're dividing each of these by 3. 3 divided by 3 is 1, so that's x. 7 divided by 3 is 7/3. And remember, this is really, I guess if we wrote it strictly speaking in the slope x-intercept form, it would be f of x equals 3, parentheses, x minus a negative 7/3. So negative 7/3 is actually the x-intercept. So notice if you put in negative 7/3 here for x, this is 0 times 3 is 0. And notice that the slope x-intercept form is a factored form. Okay, it has the slope times a factor, x minus the root being the x-coordinate of the x-intercept. And so we see that. So the slope x-intercept form and the slope y-intercept form are unique forms. The point slope formula, there's a version of that for every different point. So here's a little exercise for you. Here are 3 different functions, f, g, and h. And we have a little table here. Determine if these are linear functions, exactly linear functions or not. If they are, give the formula in the most standard form, which is the slope y-intercept form. And if they're not linear, then just say they're not linear. And how do you know? So this is an exercise you should be able to do at this point. So let's go ahead and do this now and then come back and check when you're done. Press pause now. Okay, well, what we want to do is find the slopes and see if they're the same. So technically I should have had this table lined up so the 2 is between the 3 and the 5 here, but the way my tables allowed me to do it in this software, I couldn't do that very easily, so I just put it down here. So from 3 to 5 is a delta x of 2. In other words, 5 minus 3 is 2, 8 minus 5 is 3, 12 minus 8 is 4. So here we're going up by 2, then by 3, then by 4. And then how much are we going up on the y's? Well, 6, 9, and 12. And then we don't really care about those things specifically. What we really care about is the slope after we divide these. So the m is delta y divided by delta x. So this first one is 6 divided by 2 is 3. Then 9 divided by 3 is 3. 12 divided by 4 is also 3. So the fact that these slopes are the same, this last column, that makes it linear. Constant slope makes it linear. And specifically it's m of 3. I use the first point, 311, use the point slope formula to figure this, write this down. F of x equals 3 times parentheses x minus the 3 plus the 11. Distribute, and we get 3x minus 9 plus 11 reduces to 3x plus 2. So f of x equals 3x plus 2 is the slope y-intercept form. And you could check that out and make sure that this works. Let's just check a couple of points. 3 times 12 is 36 plus 2 is 38. 3 times 8 is 24 plus 2 is 26. Let's check them all. 3 times 5 is 15 plus 2 is 17. 3 times 3 is 9 plus 2 is 11. So that does check out. Look at the next one. The delta x's are, let's see, 5 minus a negative 2 is 5 plus 2, which is 7. So negative 2 plus 7 is 5. Then we go up 2, then we go up 5. And then negative 4.3 minus 6.2 is negative 10.5. So we went down 10.5 from here to here. And from the second to the third one, we went down 3. And the next one we went down 7.5. And when we divide those out, negative 10.5 divided by 7 is negative 1.5. Negative 3 divided by 2 is negative 1.5. Negative 7.5 divided by 5 is, again, negative 1.5. So the slope is negative 3/2 or negative 1.5. And since that's the same every time, this is linear. Oops, that's a typo. That should say negative 1.5. It's constant and it's linear, so g of x is negative 1.5 parentheses x minus a negative 2, or x plus 2, plus the 6.2. That's a point slope formula. And to get the slope y-intercept form, we just distribute and combine like terms. So this is negative 1.5x minus 3 plus 6.2 is 3.2. So I believe that is correct. This next one we get at delta x is 1, then 6, then 2. Delta y is 2, then 12, then 3. 2 divided by 1 is 2. 12 divided by 6 is 2. Now those slopes are the same, so these first 3 points are on the same line. Of course, any 2 points will be on a line, but this time all 3 of those are on a line. But look at the fourth point. The fourth point doesn't lie on the same line because it has a different slope. So since the slopes are not all the same, this is not a linear. So we don't know what the formula for this might be, but we know it's not a y equals mx plus y sub 0 form. It's something else, because this is not linear. Alright, let's summarize what we know about linear function characteristics. Linear functions are functions with a constant average rate of change, that is a constant slope m. For a linear function, the slope between any 2 points is the same. It is constant. It doesn't change. So the slope is constant, and remember the slope is defined to be delta y over delta x, that is y2 minus y1 over x2 minus x1, where x1, y1, and x2, y2 are the 2 points that are on the graph in the table. The graph is a non-vertical, continuous, straight line. By the way, you could have a vertical line, but it won't be a linear function then. It would be a linear relation. We've already studied those. Those look like x equal a constant, and we know what those constant relations are that are not functions. Okay, but anything that we're talking about here is a linear function, including horizontal lines. Horizontal lines are just ones with a slope of 0, and that reduces to a constant function. But anyway, when you move to the right 1 unit on the graph, from any point on the graph, you will move vertically m units. Of course, if m is positive, that means the graph is going up when you go to the right, so that's an increasing function. So it goes up and to the right, okay? And whereas if m is negative, when you go to the right, you go down. Of course, m is 0, you go neither up nor down, and that's a horizontal line. In a table, we're adding equal amounts to the input. If your table is set up that way, then you're going to add the same amount each time to the output. Specifically, if you're adding 1 each time to the input, so delta x is 1, then delta y is the slope. It's the constant amount added to each output to get the next output. It's that common difference that you have each time when delta x is 1. So this just shows up in the recursive relationship that f of x is f of x minus 1 plus the slope m. Now we have formulas or equations of several forms, and in all these forms, m, the lowercase m, is going to be the slope. We have a slope y-intercept form, sometimes called the standard form, and that's f of x equals mx plus y sub 0. And notice that 0 comma y sub 0 is the y-intercept, regardless of what m is. If you plug in x is 0, m times 0 is 0 plus y sub 0 is y sub 0. So 0 comma y sub 0 is the y-intercept. Y sub 0 is the y-coordinate of the y-intercept, which is why we call it y sub 0, because it is y of 0. We also have a slope x-intercept form. That's the factored form. That's f of x equals m times x minus x sub 0. And in this case, x sub 0 comma 0 is the x-intercept. Okay, so in other words, if we plug in x sub 0 here for x, we've got x sub 0 minus x sub 0 is 0, times m is 0, so we get y is 0, and we see that is a point on that graph, regardless of what the slope is. And so this turns out to be a factored version, and so x sub 0 is the x-coordinate where y is 0. Okay, so notice y sub 0 is the y coordinate when x is 0, x sub 0 is the x coordinate when y is 0. The y coordinate of the y-intercept and the x coordinate of the x-intercept. We also have a point slope form for every single point. So if we take a point x1, y1, the point slope form is f of x equals m times parentheses x minus x1, close parentheses, plus y1. Notice that the point x1, y1 is on this graph. It satisfies this equation. If we plug in x1, we got x1 minus x1 is 0 plus m, or times m is 0 plus y1 is y1. And so when we have an input at x1, we have an output of y1, and that tells us that x1, y1 is a point on that graph in that table satisfying that function. The m is the same in all the forms, and again, it's the vertical change divided by the horizontal change. We haven't mentioned this one before, but there's also another form that's sometimes referred to as the general form. It's ax plus by equals c, where a, b, and c are constants. This one's not really as useful as the other three because in the other three forms there are things that you can read right off of it. The standard form, you can read the slope and the y-intercept right off. The factored form, you can read the slope and the x-intercept right off of it. And the point slope form, you can read the slope and one of the points directly in the numbers that are in the formula. But the ax plus by equals c, you can't really tell. The a, b, and c are constants. You can't just look directly at those numbers, a, b, and c, and tell anything about this except that it's a straight line. Now, you can manipulate it pretty easily. For example, if you want to find the x-intercept, you just let y be 0, and you can see that the x-intercept is going to be when x equals c over a. And if you want to find the y-intercept, you let x be 0, and you see the y-intercept is when y is c over b. And if you want to find the slope, you could solve this for y and find that the slope is minus a over b. So you could come up with these formulas, but directly it's not directly. The a, b, and c don't directly show up on the graph, but all these others show up somewhere on the graph. And one more thing before I go to the next slide. If you just see something talked about as the slope-intercept formula, they're talking about the standard form, that is the slope y-intercept form. So that's called the slope-intercept form. The slope x-intercept form is often called either the factored form or the slope x-intercept form. So again, here are different versions of the formula. So with the exception of the general form, these first three forms here tell us something that can easily be seen on a graph. So let's look at an example here. And here's an example of a graph. And I picked this one so it has some nice integer values for most of our key things. So if you look at this, the y-intercept is, well, if we want to find, just looking at this graph, if we wanted to find an equation for this, we could find 2 points that are lattice points. That is, points where they cross at a grid, where the grids cross, so that both coordinates are integers. And so notice I have a couple of those marked here. This point B1 is the point 2, 1, and the point B2 is the point 6, negative 1. So I can use those 2 points to find the slope. Notice that we're going to the right 1, 2, 3, 4, so delta x should be 4. We can see that by 6 minus 2, which is x2 minus x1, that is 4. So delta x is 4. You can see that in the table over here. Delta y then, when we go to the right, 4, but then we're going down 2, so delta y should be negative 2. We should see that by y2 minus y1, so that's negative 1 minus 1 is negative 2, and so that's delta y. If we want to find the slope, then we divide. Delta y divided by delta x, negative 2 divided by 4, reduces to negative 1/2, or negative 0.5, and that's the slope, which you also see in the table here. So now we know the slope. We can also see that slope as every time we take any point on the graph, like say this one at 0, 2, we go to the right one, we go down 1/2. Right one, down 1/2. Right one, down 1/2. Right one, down 1/2. Right one, down 1/2. Everywhere we go, of any point on the graph, when we go to the right one, it goes down 1/2. That's what makes it straight. That's what makes it a line. We'll look at some later when we don't go up and down by the same amount each time, where the slope's not constant. You'll see those won't be lines. Okay, so let's go on and look and see how we can see all the different forms here. So, for example, if we use this point 2, 1, we can do a point slope formula there. It's y equals, the first blue equation here, y equals negative 0.5 parentheses x minus 2, close parentheses, plus 1. That's the form y equals m parentheses x minus x1 parentheses plus y1, where x1, y1 is this point 2, 1. And so you can see that here, and you can see that when we go right 1 and down 1/2, we get another point on the graph. Okay? Okay. How about the x-intercept? Let's look at the y-intercept first. The y-intercept is 2 right here on the axis. That is actually the point 0, comma 2 is actually the y-intercept. So that means y sub 0 is our 2. And so we can do the slope y-intercept form. That's the bottom blue one here. Y equals mx plus y sub 0. That's y equals negative 0.5x plus 2. And so we can see the 2 here. And again, the slope we can see as you go the right one, you go down 1/2 each time. And that makes it work. We can also see the slope x-intercept. So the x-intercept, notice here, is 4, comma 0. So 4 is called the root, or the 0 of this. It's the x-coordinate that gives you a y of 0. And that's 4 comma 0 is the x-intercept. And so there we go. And so the formula for this then in the x-intercept slope form is y equals m times parentheses x minus the root. So it's y equals negative 0.5 parentheses x minus 4. And we can see again the 4 here, and again the slope you see is go the right one, go down 1/2 each time. We can see our table over here, and I started at negative 15, and it turns out to be 9.5. And every time we go up 1, so to negative 14, we go up 1/2 to 9. Negative 13, up 1/2 to 8.5, and so forth. And of course we would see, among other places, the point 0.2, the point 2.1, the point 4.0, and the point 6, negative 1. And notice each one of those, when I go to the right 2, I'm going down 1. That's another way to think of that slope. Think of it as 1 over negative 2. No, negative 1 over 2. So it says when we're going to the right, that's delta y over delta x. So right 2 and down 1. And that's another way to see the graph. And we can see that every time we go right 2 and down 1, we get another point on the graph. That's sort of skipping every other one here. So like we start at negative 14.9, we go up 2 on the x's, we go down 1 on the y's. Alright, here's some exercises for you to do, and these are all dealing with these basic concepts of linear functions. So for each of the following situations, find the equation of the linear function with the given characteristics, and I want the equation in slope y-intercept form, slope x-intercept form, point slope form. Use the point that's there if it makes sense, or just pick a point and use it. And then also graph the function and produce a table starting at negative 15 and delta x is 1. Okay, so here's 6 exercises for you to do. So you're starting with different given information, and you're coming up with all of this structure for this particular linear function. So 6 different answers, sets of answers, 6 different scenarios. Go ahead and do this. Come back when you have them done, and we'll check your answers. Press pause now. Okay, so the first one, we have a y-intercept of 0.5 and a slope of 2. That's pretty easy to get the slope-intercept form. It's just y equals 2x plus 5. That's the bottom one here. Y equals 2x plus 5. Easy to do. And of course, to graph that, we put a dot here at 0.5. Slope of 2 says we go the right one and up 2. Or if we're going to go left one, we'll go down 2. And you can see some points there on the graph, and a straight edge then connects those up. Okay. I can also pick another point on here, like if I pick the point, 1, 7. Notice if I go the right one here, I go up 2, and that would give me the point 1, 7. And so I can use that to center my line up. Y equals 2, parentheses x minus 1 plus 7. So there's a point slope formula centered at 1, 7. You could center it up at any point you want. How about the x-intercept version? Well, the x-intercept here is at negative 2.5. Now, how did we figure that out? Well, we could just take y equals 2x plus 5 and plug in 0 for y. So subtract 5, divide by 2, you get x is negative 2.5. And so we have our x-intercept there. That's the x-coordinate of the x-intercept. So the x-intercept version of the line with the slope is y equals m parentheses x minus the root, the x-coordinate of the x-intercept. So it's y equals 2 parentheses x plus 2.5. X minus a negative 2.5 if you want to write it that way, same thing. And here's the start of our table. Negative 15 matches up to negative 25, and when we add 1 to x, then the y's are going to go up 2 because the slope is 2. Okay, how about an x-intercept of 7, 0 and a slope of negative 8? Well, then obviously the same place to start here is the x-intercept slope, the slope x-intercept form, which is y equals m parentheses x minus the root. So x minus x sub 0. So it's y equals negative 8 parentheses x minus 7. And so we see that here on the graph as the 7, 0 on the x-axis. And we see the slope of negative 8, it's a right 1 down 8. This particular window is not a really good window to see this, but there it is. If you go the right 1, you go down 8. So by the way, that should give us the point 8, negative 8. And that's a point I'm using to center up the point slope formula. So it should be y equals negative 8 parentheses x minus 8 minus 8. There's a lot of 8's there, but the first one is the slope, then minus, then the 8 here is the x-coordinate of that point, and the negative 8 over here is the y-coordinate of that point. Okay, how about the y-intercept? How do I find that? Well, I could take this version here, and the y-intercept is when x is 0, so I plug in 0 for x. We get 0 minus 7 is negative 7 times negative 8 is positive 56. So 0, 56 is the y-intercept, so y sub 0 is 56. So the y-intercept, slope y-intercept form is y equals negative 8x plus 56. So if we went up here far enough on the y-axis to 0, 56, we would see where it crossed the y-axis. Alright, how about if it goes through 3, 7 and has a slope of negative 3/4? Negative 3/4 is negative 0.75, which is what I used here, but I could have done it in fraction form. Actually, one of these is around this 12.33 should be 12.3 repeated. Let's round it off a little bit. Let's see here. This one we have a slope and a point, so we'll start with the point slope formula. Y equals negative 3/4 parentheses x minus 3 close parentheses plus 7. That's the slope-intercept form. The point-slope form. We could take this and distribute and get the slope y-intercept form. So we got our negative 3/4 x. Let's see, negative 3/4 times negative 3 is positive 9/4 plus 7. That's 9.25. 9 and 1/4. Okay. Or you could do it in fraction form, 37/4 if you'd rather. Okay. To get it in, so then we know that the y-coordinate of the y-intercept is this 9.25. Okay, if we look at the slope x-intercept form, we need to take this either one of these, and plug in y as 0 and solve for x. So if we plug in 0 here, we get a negative 9.25 divided by negative 0.75. It's a positive 12 1/3, so this should be a repeating decimal here. And notice that the slope is negative 3/4, so if you go to the right 1, you go down 3/4, or if you go to the right, let's see, if you go to the right, where is it? 3/4. So if you go to the right 3, you go down 4. And you can see that on this graph here. Suppose it goes through 2 points, 2, 5, and 7, 11. And I can't see both of these on this picture here. I should have gotten to maybe a different window here. But if you just put those 2 dots in a straight edge, you've got your graph. So that's pretty easy. What's the slope of that? Well, 11 minus 5 is 6, so that's delta y. 7 minus 2 is phi, so that's delta x. So the slope is delta y over delta x. That's 6/5 or 1.2. And so using that slope in one of these points, like the 2, 5, I get the point slope formula. Y equals 1.2, parentheses x minus 2, close parentheses, plus 5. Also, I could have said y equals 1.2, parentheses x minus 7, close parentheses, plus 11. That would work too. Or lots of other points I could have chosen. So taking that particular equation there, we can find the y-intercept by, or slope y-intercept form by distributing and combining like terms. So we distribute, get 1.2x, that's here, and then we get minus 2.4 plus 5 is 2.6. So 0, 2.6 is the y-intercept, and y equals 1.2x plus 2.6 is the slope y-intercept form, or just sometimes called the slope-intercept form, or perhaps the standard form. The slope x-intercept form, or the factored form, we can find the x-intercept by taking any one of these here and plugging in y 0. We get negative 2.6 divided by 1.2 is, I think that's 2.16 repeating actually. So that should be, that's rounded off in this case. Be better to write it as a fraction really, or a repeating decimal. Okay, and so you can see all those things here, see if it makes sense. For example, the x-intercept is supposed to be negative 2.17. Does that look right? 2 1/6 actually, right there. That looks good. And then the y-intercept is supposed to be up here at 0, 2.6. Does that look right? Yeah, that looks pretty good. We don't have that point over here at 7, 11, but if we did, hopefully it would go through that point up here. And the slope we see as 1.2. From anywhere on here, we go the right one, we go up 1.2. Right one, 1.2, right one, 1.2, and so forth. Goes through 3, 6 with the same slope as 3x plus 2y equals 8. Well, if we take this 3x plus 2y equals 8, solve for y, and get it in the slope y-intercept form, let's see, we would subtract 3x from both sides and divide by 2 and distribute, we get negative 3/2 x plus 4. So the slope of that line, the line that's given, is negative 3/2. And the slope of the line we're looking for has the same slope, so it's also negative 3/2. And then it needs to go through 3, 6, so negative 3/2 is negative 1.5. So I wrote it as y equals negative 1.5, parentheses x minus 3 plus the 6, centering on that point there. And so we should see that as a 3, 6 here. We should see every time you go the right one, you go down 1.5. Right 1 down 1.5, or in other words, right 2 down 3. And that gives us a point here, for example, at 5, 3 also. Okay, the x-intercept and y-intercepts, okay, distribute, combine like terms, you'll find the y-intercept automatically. So this is negative 1.5x, and then what about the constant term? So negative 1.5 times negative 3 is positive 4.5 plus 6 is 10.5, so 0, 10.5 is the y-intercept. If we extend this graph up, this would cross up here on the y-axis at 10.5, 0, 10.5. And the x-intercept, you can actually see that right here, it's at 7, and we can see if that works out because plug in y is 0 and solve for x, put in 0, say here, you get negative 10.5 divided by negative 1.5, and that turns out to be 7. So that does work out there, and you can see it on the graph. So this is y equals negative 1.5, parentheses x minus 7. Notice that in our table, when we add 1 to x, we're adding the slope each time, which is a negative 1.5, so we're going down by 1.5 each time. This time we're given the slope is negative 1/2, and the same y-intercept is this line. This is the same given line we had last time. So here it is, and we see the y-intercept is 0, 4, but now this one's going to have a different slope. So if we graph this line and this line, they're going to cross at the point 0, 4, but different slopes. This one has slope of negative 1/2, the one we're looking for, which is the one that's graphed. So we just have this, y equals negative 0.5x plus 4. We get that straight away by pulling the y-intercept off of this line and this slope here and using the slope y-intercept form. We can find the x-intercept, which looks to be 8 right here by just looking at the graph. but let's see if it's exactly 8. We put in y is 0, subtract 4, then divide by -1/2. Sure enough, you get positive 8 out of that. So that the slope x-intercept form is y equals -1/2 times parentheses x minus 8. Or, in decimals, y equals -0.5 parentheses x minus 8, close parentheses. We can center up at any point. I just happen to scoot this over to the right one from the one we started with. We started at 0, 4, and if you go the right one, you go down 1/2, so that would be 1, 3.5, and I use that one here. Y equals -0.5 parentheses x minus 1 parentheses plus 3.5. You could have chosen another point. For example, if you'd gone over here to 2, 3, you could have gotten one with some integer values there. Of course, the slope's a fraction or a decimal there. Okay, so you can see all of these things on the graph. Okay, so we will look next time in the next part of this video, next part of this lecture, the second video on it. We're going to look at some real-world applications where we take these concepts that we've been looking at and apply them. But now you should be able to look at and understand the structure of the formula, the table, the graph, different kinds of formulas, slope y-intercept, slope x-intercept, and point-slope formula. Understand the structure of all the constants and the structure that's built in all those formulas in the table and the graph, and understand how they all connect together. And we're going to see next time if we can see how to put those together in a real-world setting.